good afternoon to all the participants for the 5th AFOMP webinar. As you know, due to the unprecedented situation because of the COVID, the in-person physical meetings could not be taken place, and therefore since June, we have started AFOMP webinar. The webinars are being organized by the chair ETC and also supported by the chair PDC and all other AFOMP EXCOM. Unfortunately, because Jin was stuck up in his official work, he could not be here. So again, I am introducing you the 5th webinar of the AFOMP. Today, we have the speaker, Dr. Chai Hong Yong from Malaysia, and he is also chair of the Professional Development Committee, and she'll be talking about the nuclear medicine requirement and all. To moderate this session, we have Jaya Singham from Jaya Singham from Colombo University. Is a senior lecturer in nuclear physics and medical physicist working very hard, and also the member of the science committee. This webinar is getting recorded. If you have any question, you can put your question into the question chat box. The moderator will collect the questions and he will put to the orator of today's webinar, and we'll have a lively discussion. This webinar is accredited, and this 1 hour webinar will fetch you 2 CME CPD points. For that, you have to write to the PDC chair, or the link will provide in that thing. Further, we, as you know very well, that there's a 20th anniversary, and on this 20th anniversary, a lot of activities we are doing. So please keep on visiting the AFOMP website. For the next year also, we are planning to continue this webinar from January to June 6 months, and the schedule will be soon available. With this short introduction, and welcome you all the participants, the speaker, the moderator, I hand over the floor to the moderator, today's moderator, Jaya from Colombo, Sri Lanka. So this is your time, Dr. Jaya.
Okay, thank you very much, Professor Aaron Chocolate, for your kind introduction. So, ladies and gentlemen, so may I have your attention? So, good morning, good afternoon, good evening. So, let me leave to share my slides. Yeah, the presentation in today's webinar is about establishment of nuclear medicine facilities and radiopharmaceutical in nuclear medicine. So this is very important topics because nuclear medicine facilities are still under development in developing countries. So nuclear medicine uses a small amount of quantity of radioisotope injected into your body to finding, evaluate, or treat a variety of disease. The patient radiation dose is very low in nuclear medicine, nuclear imaging compared to other imaging modality like CT. So, lack of medical isotopes production facilities and its short half-life are limited the nuclear medicine services in the developing countries. So, this presentation will give you an opportunity to learn about current status of nuclear medicine facilities and way to improve the current practice in your countries. So it's my pleasure to begin this event by introducing Professor Dr. Chai Hong Yang. She is currently an associate professor at the Taylor University, Malaysia. In 2005, she obtained her BSc honors in health physics from University of Technology, Malaysia. She received her master's in medical physics in 2007 from University of Malaya, and she has obtained her PhD in 2012 from University of Malaya. The Dr. Yang is a medical physicist and a certified radiation protection officer. She is one of the few medical physicists in Malaysia who complete the IAEA clinical training in diagnostic radiology. She has several additional responsibility in international and local organization as well. Dr. Jiang is currently chairing the Professional Relation Committee of the AFOMP and a web subcommittee of IOMP. She is also elected Vice President of the Southeast Asian Federal of Organization of Medical Physics, CFOM, and the founder member of the Asian College of Medical Physics. Currently, Dr. Jiang is leading the non-communicable disease research cluster at the Taylor's University. She is also focusing research to other areas such as image-guided cancer treatment, 3D printing in medicine, radiomics, and as well as radiation protection and optimization. She has already won several local and international awards for her research works, including a Certificate of Merit Award by the European Society of Radiology. She has received this in 2012. She was the first Malaysian to receive such a very high status award in history. Dr. Jiang has already published more than 50 peer review articles, 2 academic books, and she has written 2 book chapters. She currently the 3 patent drive from her research. Finally, she has been regularly invited to talk at many local and international conferences. She also serves as a reviewer for several international journals. So now I'm going to invite Dr. Chai Hang Jiang to deliver her talk. The participants, you can drop your questions in the chat box during the presentation, anytime during the presentation. So your questions will be taken by Dr. Jiang at the end of the presentation in the priority order. So please keep your mic in mute. So thank you very much for giving this opportunity. Now I invite Dr. Jiang to deliver her lectures. Thank you.
Thank you so much, Dr. Jaya, for the very kind introduction. And good morning, good afternoon, and good evening to everyone. My name is Chai. I'm going to share my screen now. Let's see if it works. Do you see my screen now? Okay.
Yes.
Great. Okay, great. Thank you very much. Yeah, before I start, I also like to wish because today is the Mid-Autumn Festival in the lunar calendar. I wish those who are celebrating a happy Mid-Autumn Festival. So I'm from Malaysia. This is the topic of my presentation today: establishment of a nuclear medicine facility and radiopharmaceuticals in nuclear medicine. These are the contents. We'll briefly go through the history of nuclear medicine. I think history is very important to know how we got to where we are, and the current status of nuclear medicine, some development in radiopharmaceuticals, and the main topic is the establishment of a nuclear medicine facilities. I will go through some local and international guidelines as well, and emergency preparedness as well as future development. So most of the contents of my talks are acquired from these resources: the IAA Human Health Campus, AAPM Task Group 108, NCRP, and the ICRP documentation. I also have adopted some contents from our local guidelines from our Ministry of Health. So let's go through the history of nuclear medicine. So the history of nuclear medicine can be traced back to 1890s, where Henry Becquerel and Marie Curie first discovered radioactivity. Henry Becquerel discovered the uranium, and Marie Curie discovered radium and polonium. And polonium is named after her homeland. And in 1930, Ernest Orlando Lawrence developed the first cyclotron. And in 1937, Carlo Pereira and Emilio Sicker, they discovered the methods of isolation for technetium 99M. And later in 1946, there was the first radioiodine treatment for thyroid cancer by Dr. Salhertz. Dr. Salhertz is an American physician, and he is now known as the founder of nuclear medicine. And later on also, we call him as the father of theranostics. In 1957, Howell Engel developed the first gamma camera, and it's named after his name, Engel Gamma Camera. And 1 year later, Walter Tucker, Margaret Green, and Pova Richards, they developed the technetium 99M generator. And in with the combination of the gamma camera and the technetium generator, it started the widespread use of nuclear medicine. In 1973, Michael Pogosian, Michael Phelps, and Everett Hoffman developed the first PET scanner. So, I'm trying to use my laser pointer, if you can. Do you see my mouse movement?
Yes.
You can see my mouse movement, is it?
Yes.
Yeah.
Oh, okay, that's great, that's great. Okay, so what about the development in radiopharmaceuticals? So as mentioned earlier, in 1930, we have the first cyclotron. So it can be used to produce carbon-11, 418, which is used for PET-CT scan, gallium-67, and so on. 1940, we have the first reactor. This is to produce carbon-14, phosphorus, and so on, as well as the molybdenum-99, which is the mother source for technetium. In 1950, we have the first automated scanner for thyroid gland, and also the Engel gamma camera, as well as the technetium generator. And in 1960, it was the gallium-67 being first introduced for soft tissue tumor imaging. And this is very useful for lymphoma, lung cancer, and brain tumors imaging. In 1970, we had thallium-201 for heart scan. And also during this time was the first PET scanner prototype developed. And later on, we used 418 for glucose metabolism in human brain imaging. 1980, we have iodine-131 MIBG for diagnosis and treatment of childhood cancer, as well as technetium 99M MIB for myocardial perfusion scan. In 1990, we have micro-PET, but this one mainly used for preclinical imaging as well as research. We had a rhenium-188 generator for bone pen treatment, as well as starting the broader application for the therapy nuclear medicine by using radionuclides, which are mostly beta or alpha emitters. We also have, I'm sorry, the timing is out. Okay, we also have radiolabeled antibodies, as well as starting of the alpha particle therapy. And in 2000, in the last decade, we have seen the very rapid development in radioimmunotherapy, theranostics, as well as molecular imaging and therapy. So what about in the next decade? What you think? So this is just my personal view. These are all the active areas in research currently, and I would think that the coming decade, we will be more focusing on personalized dosimetry, the treatment planning software, as well as artificial intelligence. So the application of nuclear medicine can be generally divided into 4 areas. First one is the non-imaging studies. That includes the thyroid probe that we use for thyroid uptake studies. And also the gamma camera or the radioimmunoassay is a very effective method for the detection of some biomarkers. Then we have diagnostic imaging, which can be further divided into planar imaging or SPECT imaging. Then we have hybrid machine, the SPECT-CT, followed by PET-CT, PET-MR, and now we have even SPECT, PET, and CT hybrid. And in nuclear medicine therapy, so, it can be divided into targeted radionuclide therapy, radioimmunotherapy, and selective internal radiation therapy. And the more recently is the theranostics. Theranostic is the combination of therapy and diagnostic application. And this is an approach towards the personalized medicine. So in summary, the development of nuclear medicine rely on the 3 key factors. First one is the production of radionuclides. They include the nuclear reactor, the particle accelerators, as well as the generators. Second is the chemical process to synthesize the radiopharmaceutical for imaging and treatment. And lastly is the instruments, which is the camera that can detect radiation emitted from the body. And these are the current technology, started from gamma camera. Then we have SPECT camera. Basically, these 2 are the same, except the imaging technique is different. Then we have SPECT-CT as well as SPECT-CT. And also, we also have dedicated SPECT scanner, such as the cardiac SPECT. And we have PET-CT, and the more recent one is the PET-MR. And these are the latest development. I'm not sure you have seen the machine or not, but some of them are already in the market. Some are still under the studies. The first one is the S-Flex. S-Flex is the camera head can be positioned at freely for flexible imaging, especially useful for patients who cannot move on the table. And we have brand spec, which can give an image resolution of 2 millimeters. And then this one is interesting. This is adaptive specity, and the detector head can actually go in and out automatically, follow the size of the patient. And the last one is the SPECT-CT PET hybrid camera by AnyScan. In terms of radionuclide availability, I would like to show you this very interesting image, pictures from Blover. It's called a nuclear chocolate box, the periodic table of nuclear medicine. It's a very nice representation of the radionuclides that are currently in use in nuclear medicine. So I just give a few examples here, like rubidium-82, used for cardiac scan. Technetium-99M is here. Samarium-153, Thorium-18, Lutetium-177 for theranostic, and there is Polonium-210. And you can see a skeleton there because there was an incident of radioactive poisoning using polonium about 10 years ago. So I'm sorry for the low resolution image, but if you're interested, you can write to the author to get a more clear image. So this is the main topic of my talk today. To establish a nuclear medicine department, we need to do a very thorough planning. So it should include all these components, these 5 components. First is the organization and the management structures. Second is the very detailed SOP documentation on the clinical services, SOP on the use of radiopharmaceuticals, SOP on radiation safety and security, as well as the site and the architectural design. I'll go through it one by one in my coming talk. So let's start with the organization structures. Starting from the head of department, assisted by the administrative staff, and the service can be divided into 2. One is the clinical services, one is the medical support services. So under clinical services, we have nuclear medicine specialists. They are assisted by medical officers, nuclear medicine technologists or radiographers, nuclear medicine staff nurse, as well as the attendants. Whereas under the supporting services, there are nuclear radiopharmacists, radiobiochemists, as well as nuclear physicists or medical physicists. So since most of us here are medical physicists, so what is our role as a medical physicist in a nuclear medicine department? I have listed out the responsibilities here, but I will not go through it one by one. But in general, our responsibilities involve in radiation safety, and not only for patients, also for the staff and the member of public, as well as in the development of the quality assurance program for the whole department. So we're responsible as a radiation protection supervisor or the radiation waste management officer. We need to ensure the process of procurement of the radioactive items fulfill the legal requirements. We are responsible for the acceptance and storage of radioactive materials. We also need to monitor the radioactive materials packaging, labeling, and the transportation. We are responsible for the cleanup and monitoring of radioactive spills. And we need to ensure the decontamination activities are conducted according to the proper procedures. We need to monitor the supervised and control areas. And we need to monitor all the radiation workers' radiation dose record, and also make sure they attend the required periodic medical examination. We need to investigate radiation exposure for any accident or contamination. We need to notify and report all the abnormal exposure to the relevant authority. And we might also involve in the monitoring of patients undergoing therapy. And also, we might involve in the planning of facilities, equipment, commissioning, and decommissioning. We are responsible for the preparation of specification, acceptance tests, and the QC of the equipment. We provide first-line maintenance and help to identify and resolve the equipment problems in liaison with the services personnel, such as the engineers. We also involve in management of scientific and technical aspects of the services. We are responsible for the overall supervision. Usually, we are tasked to help to monitor the service for the computer system management, to provide advice on computer use, as well as the first-line support for application in software. We can also involve ourselves in providing the technical advice and assist in the quantification and dosimetric calculation. Okay. Lastly, we also need to participate in the teaching and training program, as well as the CPD training, such as what we are doing now. And we also need to involve ourselves in R&D as necessary for the practice of nuclear medicine. And here I would like to highlight that the IAEA that has provide a very excellent support to the developing countries in related to nuclear services. So these are some textbooks available in the IAEA website. And basically, most of the resources available on the IAEA website are free to be downloaded. So there is a nuclear medicine physics handbook for teachers and students, as well as there is a clinical training of medical physicists specializing in nuclear medicine. This is in parallel to the ROM as well as the DRMP training. And also, if you are interested, there is one particular section just for medical physicists. And here should contain all the information that is necessary for a medical physicist to refer. And next, where to find resources? For example, here is the guidelines if you want to establish a nuclear medicine facilities. So here are the resources. These are the international organizations who provide reliable information. The first one is the IAEA Human Health Campus, European Association of Nuclear Medicine, Society of Nuclear Medicine and Molecular Imaging based in US, as well as your own local policy and guidelines. And here I show this screenshot of the IAEA website. This is the IAEA Nuclear Medicine QC Toolkit. IAEA has been very generous in sharing all their resources, and unfortunately, I have seen like not many people aware that actually here in the IAEA website, there are some free videos for us if you want to have like self-directed learning. And also they have a platform called Ample that we can get a lot of online teaching resources to help us to improve our professional services. And in this case, this particular example is the Nuclear Medicine QC Toolkit. So you can basically download it for free, and you can it's a ImageJ plugin, and you can use this software for the simplified analysis steps when you are doing the QC for the nuclear medicine machines. Okay, so next is the SOP on radiation safety and security. This is important, so I will list it down here. So the document should include the radiation safety of staff, discharge of radioactive patients, and protection of general public. This includes the guidelines for hospitalization with isolation. For example, iodine-131, if the administered dose more than 1,100 megabecquerel, the patient has to be watered. And the guideline for discharge patient with restrictions, as well as discharge the patient without any restrictions. Use of public transport by the discharged radioactive patients. Managing death of the radioactive patients. Order, purchase, transportation, and security of radioactive source. Radioactive waste management, and we also need to include the radiation accidents. If in case of accidents, what should we do? This will cover like maybe wrong radiopharmaceutical use, any therapeutic treatment delivered to the wrong patient or the wrong tissues, or the patient is treated with a dose differed by 10% from the prescribed dose, or any diagnostic exposure more than 50% than the intended dose. And also in the document, in the SOP, we also need to include the possibility for major radiation incidents, such as theft, loss, or sabotage of any radiation source, contamination on individual that required medical treatment, and also for the contamination, which is more than 5 times of the annual limit intake. And management of radioactive spills, this can be divided into major spills and the minor spills. Major spills, the example of the radiation level is different for different types of radionuclides. For example, 10 millicurie of 418, 1 millicurie of iodine, 100 millicurie of technetium, and so on. We also need to include the management of radiation monitoring equipment failure. In case of the breakdown, what should we do? And management of radiation hazards in a fire accident. So next is the architectural design of the nuclear medicine department. So these are the key components that we must consider. First is the space, the power, the floor loading concerns, as well as radiation shielding. The first one is traffic patterns should be designed to keep the movement of the radiative source, including the radioactive patients, away from the staff, unrelated patients, or the member of public, and also the sensitive imaging equipment. The area shall be arranged in an increasing order from the low activity to high activity. And this is a must. The radiation symbols must be displayed. This is an example of a typical nuclear medicine layout. Here is the entrance. So starting from the entrance, okay, here should be the low activity area. And towards the end of the corridor, okay, we can arrange accordingly for the area of higher activities. And if the facility has a PET-CT or a cyclotron facility, it can be extended towards the end here. And for the classification of area, we have control area and supervised area. For control areas, the example is the room for preparation of radiopharmaceuticals, room for dispensing, room for storage of the radionuclide and the waste, room for administration of the radiopharmaceuticals, and the imaging rooms are all classified under control areas. And supervised area, which is the whole department. So there is no clean area in nuclear medicine department. And next is the technical specification for shielding calculation. So here I referring to the guideline by the AAPN Task Group 108. This is a formula recommended by the task group. Okay, it looks very long and complicated. Okay, but don't worry, we'll go through it one by one. And these are the summary of the dose parameters you can read up. These are the definition, and these are the formula. Okay, so the formula looks very complicated, but if we break it down one by one, okay, we'll try to go through it together now. So the first parameter is P. So P stands for the weekly dose limit. So here we assume 50 working weeks per year. So for uncontrolled area, we will apply the dose limit for the member of public, which is 1 millisievert per year. And we divide by 50 weeks, it would be 20 microsievert per week. So this would be the dose level for the P. Whereas for the control area, the occupational dose limit applied, which is 50 millisievert per year. But most shielding calculation use a target level of 5 millisievert per year, okay, to apply the RRR principle. So if 5 millisievert per year divided by 50, we will get 100 microsievert per week. So this is the P value here for the control areas. Next, we have D. So D is the distance from the source. So for example, here, this is a PET uptake room or the scanning room. We assume the patient is sitting 1 meter above the floor. And for the officers above the floor, we assume that the officers are sitting 0.5 meters from the floor. Okay, and for the room below, we assume the standard height of a person is 1.7 meters. And for the room next to it, we assume the person is standing 0.3 meters away from the wall. So these are the distance that we need to apply in this formula. Okay, next is the tau. This is a tau. This is a dose rate constant, or sometimes we call it as gamma constant. So the unit is microsievert meter square per megabecquerel hour. And we can refer to the task group, AAPN task group, they are given us these tables that we can refer these numbers. And for technetium is this one, and the iodine is this one. Next is the T. T is the occupancy factor. So for all the control area, the occupancy factor is 1. For the adjacent treatment room, patient examination room is half. For corridor, employee lounge, and the staff restroom is 1/5. And for the treatment ward door is 1/8, and so on. So this table is also available from the NCRP 147. Then we have these parameters. So NW is the number of patients per week. So here we assume 8 patients a day, 5 days a week. So there would be 40 patients per week. A0 is the initial injector activity. So let's take the example of PET-CT. The A0 is typically 555 megabecquerel or 50 millicurie. And the T is the time. If it's in the uptake room, then the uptake time is 60 minutes. If it's in the PET scanning room, then the acquisition time we assume is 45 minutes. And from here, based on the time, we will apply the dose reduction factors because of the decay of the radioactive source. So for example, this is the table, the RT value for fluorine 18. So let's say we are sorry, can you hear me?
Yes, yes. Now we can.
Okay, great. Okay, so we have gone through all the parameters just now, one by one. Okay, and lastly, we will get this B value. B stands for transmission factors, and the table is also provided, table 4 in the AAPN task group. And by referring the value here, we can find the thickness required for the shielding. And we have to pay attention for the thickness here. If you are using lead, the unit is in millimeter. If concrete or iron, the unit is centimeters. So we have done the formula just now, the complicated formula just now, okay? And this is an example how we do the calculation. So let's take the uptake room. So at uptake room, we want to achieve a protection goal of about 20 microsievert per week. The distance based on measurement is 4 meters. Gamma constant, we can refer to the table just now. Occupancy factor is 1. Number of patients is 40. Injector activity we assume is 555 megabecquerel. Decay factor is 1. The source duration in the uptake room is 60 minutes. And hence the reduction factor is 0.831. So the reduction factor is getting from the table just now. And from here, we have all the parameters and we will get the B value. So the B value is 0.188. And by referring back to the sorry, I think my slide is gone, is it?
Yes, yes.
Yeah, slide has gone. Again, you have to
Okay.
share it again and come to that thing.
All right. Do you see my screen now?
Yes, yes.
Okay. So I need to go to. Ouch. Sorry for the technical error. Okay, so we were here just now for the uptake room. So we get the B value is 0.188 and we refer to the table, this table. So 0.188 is here, right? Here, if this is the lead, apply for lead, so the thickness that required is 12 millimeters. Okay, so therefore, the answer is 12 millimeters or 1.2 centimeter of plumbum is required, or that equivalent to 15.2 centimeter of concrete. Okay, the next example is for the scanning room, the PET-CT scanning room. Again, it's the same calculations, except the reduction factor is different because the time is different. So for scanning room, we are using 45 minutes, and in the end, we will get the p-value of 0.334, and that require a shielding of 0.8 centimeter of plumbum or 11 centimeter of concrete. Okay, so that is all about the formula for the calculation of shielding, and it's very much encouraged to use computer software. For example, Excel can actually do the work for all the calculations, because we need to calculate for every individual area, and we need to calculate for all the walls as well as the floor and the ceiling shielding. And this is an example of the report that we need to submit for the shielding requirements. So we need to have an engineering drawing, and we can use the color coding for the different shielding requirements. And of course, there are also commercial software available. And this software is called RSD, and by the company name called 511 KEV. They are based in Australia. So by using the software, do you hear me? I heard some noise just.
Yes, yes.
All right. So this software can do a great job by just key in a few numbers. Okay. So you can see you can choose the scenario. Okay. Let's say this one only the city is used without the pet. So this will be the dose map. And if there are pet patient inside the department, and this will be the dose map in the department. Okay, so this is the conclusion, the summary for the shielding calculation. So we have to make a few assumptions. And the calculation method actually is based on the most conservative approach, meaning that we are using the maximum dose possible for the calculation. And in fact, the gantry of the scanner can provide substantial dose reduction, okay, because they are shielding there. But because we are taking the most conservative approach, we don't consider that in our calculation. And for most of the new facilities, they can use concrete as the shielding material because concrete is cheaper. However, for the existing facilities, often we have to use lead, because of the space constraint. And for uncontrolled area with high occupancy should be located as far as possible from the uptake room and the imaging rooms. Separate toilets should be located for the PET patients close to the imaging room. If the uncontrolled area are located above and below the uptake and imaging room, the spacing between the floor may need to be greater than the normal. But if that is not feasible, then the floor need to be able to bear the weight of the lead shielding. So because of the requirement of shielding, most of the nuclear medicine departments are located at the ground floor. So if it's at the ground floor, then you can save the cost for the floor shielding. This is an example of it's a good design of a nuclear medicine department layout. So this is the entrance of the patient. So here will be the low activity area, and towards the end of the corridor will be the higher activity. And in the last end of the corridor is the patient toilet. Sometimes we call it as a hot toilet, but this one only reserved for the PET patient, the PET-CT patients. So the patients, once they've done the imaging, the PET-CT scan, they will use this toilet, okay, to pass urine before they go out from the department. And portable shielding. So during the planning as well, the design as well, we need to consider, okay, to buy additional portable shielding. Okay, this includes the lead containers as well as the shielding lead bricks, just in case of any emergency. And also from the PET-CT uptake room, the FDG uptake room, if there is a constraint of space, let's say we cannot have an individual room for every individual patient, then it is also possible that we can apply the portable shielding in between the patients. And for surfaces, all the floors, the work surface, and the wall should have hard washable, non-porous, and leak-proof covering to allow for easy decontamination. And no carpet is advised. And for ventilation, we need to consider the ventilation as well, especially for the hot lab. It should be a unidirectional airflow from low activity to higher activity area. So in the hot lab, we will apply a negative pressure, meaning that the air is always flowing from outside to inside. For plumbing, it shall be planned to ensure direct flow of possible radioactive liquid effluents directly to the decay tank or to the ultimate discharge point. The drain pipes and the decay tank should be leak-proof and corrosion resistant. And for the radionuclide therapy area, it is advised to separate them from the diagnostic area and have a separate access where possible. The radiation level at the nurse station in the ward and outside of the isolation room shall not exceed 1 microsievert per hour. How we get this number? It is based on the dose limit for the member of public, which is 1 millisievert per year. And we should consider for a design for the in-house radiopharmacy hot lab. And also, we should have extra space for radioactive storage in the future. And also the radioactive waste disposal and the management shall comply with the radiation protection guidelines and the regulations. Okay, this is the shielding requirement for different facilities. So it's very much depending on what are the radionuclides that are being used. For example, if the departments only have the SPEC facilities without the PET facilities, and most of the time we are using technetium-99m. Technetium-99m, the gamma energy is 140 keV, and the HVL of lead is 0.3 mm. The 10 value layer is 0.8 mm. And this requires about 2 mm of plumbum for the shielding, as well as for the syringe shield. And for technetium-99m, because 2 mm of lead, even though it contributes to the weight, but it's still possible to do the direct injection. However, if we are designing for a PET city facilities, then 418 is applied. The energy is 511 keV, which is very much higher than the technetium. And the HVL is 6 mm. So we need, typically we need 5 centimeters of lead, okay, for the hot lab workbench. For the shielding for the syringe, typically we use about 1 centimeter of lead. So because of this 1 centimeter, it is like too heavy, okay, to be administered, to be handling. So usually for PET CT injection, for the 418 injections, we will set up the line, the catheter line, and do the IV injection through the catheter line. Okay, whereas for beta source, such as yttrium-90, yttrium-90 is a pure beta emitter. It only emits beta, no gamma radiation. We need to pay extra consideration actually for beta source, because if we use the wrong shielding materials, the beta particles will interact with the high Z material, for example the lead, and it will generate brainstem lung X-ray. So this is according to the principles of the particles interaction with metal. So when the electron go through a very high atomic numbers of atom, it will actually deflect it and it will generate the brainstem lung X-ray. So if we use a wrong shielding material for the beta source, okay, instead of giving protections, we are actually adding more hazards, more radiation hazards to the department. So for beta source, the recommended material is PMMA or plastic of about 1 centimeters. Okay, and for the iodine-131, the watt shielding. So iodine-131 is considered as the highest energy radioactive source that is being used in nuclear medicine therapy. it emits both beta and gamma radiation. The beta is 600 keV, the gamma is 364 keV, and the HVL is 0.3 centimeter, TVL is 1.1 centimeters. So for the isolation ward, because we have to, sometimes we'll administer the radioiodine pill to the patients in the ward. So we might need to transfer the source from the nuclear medicine department to the isolation ward. So we need a portable cart with proper shielding for the iodine source. And also in the isolation room, it's advisable to put the non-absorbent layer, the plastic layer on the floor, okay, under the bed and also inside the toilet, so that if in case of any contaminations, it can be easily cleaned up. And also for the lead shielding, the lead apron, the normal lead apron, the thickness is about 0.35 millimeters to 0.5 millimeters, and that is actually not sufficient to be used for iodine 131 shielding. So additional protection is needed, such as the portable lead shielding like this. So in case of the staff need to go in to check on the patients, the staff can actually stand behind the shielding. Next, I will touch a little bit about cyclotron. So this is a layout of a cyclotron facilities. So in case if the departments need to install a cyclotron, so it will be placed at the end of the corridor, but next to the PET-CT room. Okay, and next to the cyclotron, there need to be attached a radiochemistry lab, and also the QC and the dispensing room. As of 2018, there are over 1,200 cyclotrons around the world, and approximately 550 of them operate above 60 mega electron volts, and this is actually sufficient to produce technetium-99m. As we all know that technetium-99m is produced using the molybdenum generator, but currently it was happening in 2009 and also 2012 and 2013 of the world, the global shortage of the molybdenum generator. So, and then the scientists have actually developed a method using cyclotron to produce technetium-99m. And if you want to know more, there is a very thick document by IAEA. It's on the guidelines for setting up the cyclotron facilities. And inside this document, there is a table that lists out all the costs needed to set up a cyclotron facilities. So basically, to set up a cyclotron facilities, money is the first issue to consider. Okay, and how much is the cost? Based on the estimation, is about US dollars 500,000 to 600,000 per year. This is per year. Okay, and the cyclotron facilities, previously, the cyclotrons are installed inside a bunker that need a very heavy shielding of the buildings, but the modern cyclotrons are available now. The modern cyclotron is a self-shielded cyclotron like this. They are smaller and they already come with the shielding. So you don't need to add additional shielding to the buildings, to the rooms. And the recent technology, they have this one called dose on demand cyclotron, which it can only produce one dose at one time. And also there are mini cyclotron. And more recently, this is by one of the manufacturers. They have a smaller size of cyclotron, self-shielded, but with high energy. And it can be used to produce both fluorine-18 and the carbon-11. Okay, so next I would like to talk a little bit about the emergency preparedness. In the past 5 years, IAEA has actually put in a lot of efforts in this so-called EPR, Emergency and Response Plan. So they have actually done a lot of training, okay, around the world. And also there's some publications, and this is a good one that we can refer. It's a pocket guide for medical physicists supporting the response to nuclear or radiological emergency. So inside the document, there are a table here listed out what are the PPE that need to be ready just for emergency case. Okay, so it even put in the inventory here, the numbers of jumpsuits, how many gloves we need, and how many shoe covers we need, and so on. And this is a plan, the workflow. I'm not going to go to details. I just want to show you that we need to have this form. And this emergency actually includes the major nuclear accident. It could happen outside of the hospitals. It could be from the industry nuclear services as well. So in that kind of scenario, the individuals, so-called patients, they will be sent to the hospitals. So the country need to identify which hospitals should be get ready for nuclear emergency. And during the emergency, what should we do? So we should have a proper layout. Okay, when the ambulance arrive at the entrance, okay, we should actually isolate. We should actually divide the area for contaminated patient as well as the clean area. So when the patient is arriving at the hospitals, we need to have a survey point. So after we survey the patients, if the patient is contaminated, they have to go through the red zone. If the patient is clean from radiation, they will be sent to the clean area. Okay, this and also for the emergency preparedness plan, not only we need to have the documents ready to know what we should do when emergency happen, we also need to have drill, some practice, some training. Okay, and this one, some pictures, some training done in our local hospitals in Malaysia. And also it involves the whole team, not only medical physicists. And this is a micrograph, electron micrograph of the chromosome who is being destroyed by the radiation. So basically it's a fragmented chromosome here, and this is ring formation, and this is a dicentric chromosome. So this shape of the chromosome, this formation of chromosome represents the radiation effects. Okay, and the emergency plan should include the responsibility of the whole team. So it is a teamwork, and during the training as well, it should be done all together. It's not possible without a teamwork. Okay, lastly, I would like to share this one. It's a very interesting document. This is from IAEA also. For the recent pandemic, the COVID-19 pandemic. So pandemic, even though it's not radiation related, but it's an emergency and it affects everybody, okay? Everybody, public as well as hospitals, and of course the nuclear medicine department. So in case of this pandemic happens, what should we do? Okay, some important notes here about the COVID-19. One infected person can transmit to 2 to 3 people. And the transmission can be via the droplets, meaning through the coughing, speaking, or the breathing. And also, recently they suspected it will be airborne as well. And asymptomatic patients can also transmit the virus. So because of the very high rate of transmission, it's considered as a pandemic, and hence it's an emergency. These are the statistics recently published on the global impact of COVID-19 on nuclear medicine departments. So there are 72 countries involved, and also they did a survey, the questionnaire survey, on more than 200 nuclear medicine centers in the world. And it was observed that most of the departments have a decreased rate of the nuclear medicine cases. This is for diagnostic nuclear medicine, up to like 50 to 80%. So they have cut down the patients from 50 to 60%. And this is for nuclear medicine therapy. Also, it's about 50% of the patients. And this is the numbers of nuclear medicine staff who are infected with COVID-19. But in the document, it doesn't mention whether the staff is infected by the patients in the nuclear medicine department or from elsewhere. So it's difficult to trace. But fortunately, 85% are not affected. So meaning that the facilities, the nuclear medicine departments have done a good job in the handling of emergency. And also there is document if you are interested to read about nuclear medicine services after the COVID-19. How do we gear back to normal? So it has to be a very strategic planning and it has to be done phase by phase. Okay, so phase by phase means that how many patients, number of patients you control to come to the department. And how it affected us. So now we have a so-called new norm, and these are the floor for the patients who come to the hospitals now. Nowadays, when the patient come to the hospital, we have implement all sorts of filtering. So first, we need to monitor the temperature of the patient, and patients are required to wear masks, and we control the visitors and also the accompanying person. And also we apply distance as well. So this is very much applied to our principles of radiation protections, right? Like time shielding distance. Okay, so it's very much, it's a similar condition is applying here. Okay, so lastly, what is the future of nuclear medicine? I mentioned just now is I would foresee it will be the personalized dosimetry, treatment planning, and artificial intelligence. But of course, not only that, there would be also a lot of efforts being put into biology, especially radiobiology. So how radiation interact with biology. And recently there is a very interesting talk organized by the IOMP webinar on the hypoxic effect. So how the hypoxic effects affecting the treatment outcomes in radiotherapy. So we need a more extensive knowledge in radiobiology in order to understand the characteristics of cancers and how do we treat them. And also nanomedicine is very common nowadays, using nanoparticles, and maybe nanonuclear medicine. Maybe there might be a new term in the future where we are using nanoparticles but labeled with radioactive source, and we use it for diagnostic purposes. So as medical physicists, we have our direct involvement here. So this is our roles, our area. Whereas this might not be our area, but we should collaborate because everything is hybrid nowadays and we need to apply the knowledge in our areas as well. So this is how I see the future. Of course, we are all moving together towards precision medicine. Precision medicine means the 4 Ps, which is predict, personalize, preempt, and participation. So the future would be the patient come to the hospital, we collect a specimen of patients such as tissue, blood, saliva, or even the CT image or radio image. And based on that, we will run through the genomics, proteomics, metabolomics, radiomics, and so on. And the new term is called panomic. Panomic is a combination of all these omics. And in the end, we need to aggregate the data and we need to use computers help for big data analysis and so on, and in the end give us the good clinical outcome data. Yeah, so this is my last slide. Yeah, this is my last slide. I'd like to throw back the question to all of you. Is conventional nuclear medicine, or we so-called the technetium 99 imaging, going to a dead end? What do you think? Okay, thank you very much for your attention. Thank you, Dr. Jaya.
Yeah. Thank you very much, Dr. Professor Jiang, for the very informative and attractive talk about the nuclear medicine facilities and radiopharmaceutical. So now it is the time for the questions and answers. I got 3 questions from the audience. So first one from one of the participants. The question is, how can a nuclear physicist fits in terms? I will share my slides. Okay.
I'm sorry. Again, please.
Yeah, wait 1 minute. So how can a nuclear physicist fits in terms of research related to diagnostic therapy and personalized medicine, especially when one are studying under the medical doctors or radiologists. So they ask about the opportunity for the research. And
Okay, so the question is regarding how do we get ourselves involved in research, is it?
yes, yes.
Okay, and I'm not sure the specific question. Does it mean if you are in imaging, diagnostic imaging department, how do you get yourself involved in radiotherapy or nuclear medicine? Do
Yes,
I
yes.
understand the questions correctly? Okay, all
Yes.
right. So yeah, so actually multidisciplinary research is very, very much encouraged. So we now realize we cannot just do research in our own area without collaborating with others. So we should learn from each other's strength. So how to get ourselves involved? Just we have to go out. We have to go out and talk to people. Talk to our friends in other departments, and also talk to the clinicians to see what are the needs in the clinical.
Okay, thank you. Can you stop your screen sharing? Then I can share the questions. That is easy for you.
Oh, okay. So
Okay, thanks. Okay. The second question is from Bangladesh. Yeah, this is the question. So when the radioactive isotope is injected into the patient body, after few minutes, the patient will death due to the any reason, unknown reason. So by God grace, then how to handle or care this type of patients as a nuclear medicine technologist or radiologic technology physicist? So how to handle these situations?
okay, so actually this is considered one of the emergency. It has to be included in the emergency plan during the planning of the nuclear medicine facilities. So that we have to have a very proper step-by-step guidelines, like what should we do when the patient died in the nuclear medicine department. Okay, so first of all, of course, the first thing first is to inform the RPO, Radiation Protection Officer. And most of the time, the medical physicists, clinical medical physicists who work in the hospital, they also act as a RPO. So the RPO need to have a very clear mind of how to handle the situations. So they need to bring along the survey meters. Okay, first to make sure the scene is clear from any contamination or the high radiation exposure, and then further investigation can be carried out.
Okay, the third one. So please explain how are the regulations in your country regarding the previous provisions for the release and discharge of nuclear medicine patients.
Okay, in Malaysia, in my country, we have a very, very clear flaw. So for patients who are above, who are injected above 1,100 megabecquerel of iodine 131, it is a requirement, okay, requirement to admit the patient in the isolation ward. And after maybe 2 or 3 days, the medical physicist will go to the isolation ward, okay, and bring along the survey meters, and they will measure the radiation exposures at 1 meter away from the patients. So if the radiation level fall below, can't remember the exact number now, certain limit, the dose rate limit, then the patient can be discharged. If not, the patient has to be continued to stay in the hospitals until the external radiation exposure is below the limit.
So I think the last question from some other person. So please, can you give specific research ideas why collaborating with radiochemists?
Why is it? Why or
Yes,
how?
why?
Why?
How, I think how collaborating with radiochemistry? Yes.
Okay. Why then is very clear answer, because we need to integrate our knowledge together, because even for radiation treatment, we need to have knowledge in biology, physics, as well as chemistry. Chemistry because it's related to the radioactive source or radiopharmaceuticals. So that is why we need to collaborate with them so that we can, each party can actually contribute the knowledge together. And how to do that? As I say, we need to go out, we need to talk to them, we need to talk to our core colleagues in different areas to understand each other needs and the strengths.
So
Yeah, I
finally,
hope I answered.
yes, finally, I have a question. Now the technologies they improve day to day. So what about the technology versus the dose, patient dose? It's increase or decrease?
Patient dose, is it? You mean for the imaging or therapy?
Yeah. Imaging.
Imaging, of course, we can see the dose is gradually decrease, gradually. Yeah.
So with the technology.
Yeah, two reasons. One is because of the technology. Technology is the main reason actually, because of the improvement of the detectors. And nowadays we have digital semiconductor detectors, which can more efficiently, it can convert the radiation into the signals. That is the first one. And the second one is also because of all the training as well as the optimization approach that us, medical physicists, together with our colleagues are doing. Yeah.
Okay. Thank you very much again, Professor Jiang. Again, so the event was very successful. So I think we got about 100 participants. So finally, I would like to thank again AFOMP for giving me this opportunity. So now I hand over this session to Professor Anand Chokle to conclude the event. Thank you very much.
Thank you very much.
Just I'm seeing Professor Jin Xians is there, who is the ETC chair. So he will conclude and give further information. It is all to Professor Jin Xians.
Okay, thank you. Thank you both. Thank you, Professor Yang, and thank you, Professor Jia. For the last talk, nuclear medicine has played an increasingly important role in the modern medical medicine field. So today, Dr. Yang, you asked a very informative and very useful lecture. I think it's also it's very we have a very good discussion about the questions raised by the audience and answers. Now we are going to the end, so I would like to say the next I just broadcast the next webinar will come on November 5th. It's Professor Alan Bergler. He's going to give us a talk on the dose reference level. So we are. Any more questions, Dr. I think Dr. Huang is hands rising. Is there any questions, Dr. Huang? Otherwise, we will close this seminar. Okay, I think no more questions. Thank you. Okay, thank you all. Hope to see you next month, November 5th. And for the Dr. Arnold, she will give us another talk. Okay, bye-bye.
Thank you, everyone.
Thank you.
Everyone.
Stay safe. Stay safe.